So good morning, all of you. So in the last class, we have finished till viscosity, right? And now one table I want to give you, that is viscosity of some common fluids. Okay. Like this table you can make. In the first one, you write fluid, here temperature, that is in degrees Celsius, and here viscosity. Okay, make like this table. So see here, first one, that is air, and it is 0 degrees Celsius. This viscosity is in millipoise. Okay, so here I'm writing millipoise. So see here, 0.017 for air. If the temperature changes to 40 degrees Celsius, then it becomes 0.019. Next one, blood. Viscosity of blood.
Sir, just now you started.
Body temperature.
No, man.
37 degrees Celsius, and it is 2.7. Okay. And next one is glycerine. And at 20 degrees Celsius, it is 830. Next one is honey. And what are the naturally available, or in the nature, what is the temperature? At that, it is 200 millipoise.
Sir, once back page it one.
Machine oil.
Sir.
This is only first page day.
Okay, okay.
Machine oil.
Okay.
It is 16 at 16 degrees Celsius. It is 113. And if the temperature changes to 38 degrees Celsius, then it is 34 millipoise. Next one is water. Water at 20 degrees Celsius, it is 1. And at 100 degrees Celsius, it is 0.3. Now see the conclusions. First point, viscosity of liquids. You can see the table, whatever the viscosity of liquids is there, is much greater than that of gases. Yes, for example, you see here water or machine oil or honey, you see and air you see 0.017, 0.019. So this is very, very less as compared with this liquids. Yes, no? So viscosity of liquid is always greater than that of the gases. Second one, you see, as temperature increases, as temperature increases, of liquids, what happens? See, if we will increase the temperature, viscosity decreases or increases? Decreases. Yes, no? As temperature increases of liquids, viscosity decreases. You can see in case of water, at 20 degrees Celsius it is 1, but at 100 degrees Celsius it is 0.3. So as you have increased temperature from 20 to 100, your viscosity decreased from 1 to 0.3. Yes, no? So if we will plot the graph of this for liquids, you can see what happens. The viscosity decreases, and that's why your graph is something like this. Like this. Okay. Yes. Here it is viscosity, and here it is temperature. Okay. Next one. Suppose now if temperature of fluid, particularly this is liquid, finished means gases we will consider now. If temperature of gases increased, what happens? Viscosity increases. Viscosity increases. You see here, this one, in case of air, at 0 degree, you have 0.017, and at 40 degree, you have 0.019. Okay. So with the temperature or with increase in temperature, viscosity increases for gases, whereas for liquids, it decreases. Got it? Understood? So note down this. Now let's move ahead. Now some practical applications we are going to see. Practical applications to reduce the viscosity. Okay. So number one, that is shape of boat, vehicles and aeroplanes designed so that it will have less viscous force. Yes, no? Next one, phi shape of what you can say drainage, है ना? Right? No?
Yes.
Yes. Why? Because the layers are there now. V shape of canals. So as this V shape is there now, so what happens? The force between these two layers is less if area of contact is less, and that's why whatever the canals are there, we are designing in a V shape, okay, to reduce the viscous force only. Next, one more application. What we can say, highly viscous lubricant is used in machines, okay, such as a grease. Yes. Next, viscosity of blood is used to, or viscosity of blood is used to, or used in medicine purpose or in medical field, we can say. Is used to diagnose some diseases, okay. These are the some applications of this viscosity, okay. Note down fast. Yes, finished. Let's move ahead. Now some problems we are going to solve. See here, problem number 1. Write with me. A metal block of area 0.1 meter square is connected to a 0.01 kg mass via a string that passes over an ideal pulley. Ideal pulley means frictionless pulley, okay. Okay, frictionless and massless. You know this. Ideal pulley means what? Frictionless and massless. Okay. A liquid film of thickness 0.01 mm millimeter is placed between the block and the table. Between the block and table. When released, the block moves to the right. The block moves to the right with a constant speed. With a constant speed means acceleration is 0. Yaad rakho. With a constant speed of 0.085 meter per second. Find the coefficient of viscosity. Coefficient of viscosity means what? Eta we have to find. Okay, find the coefficient of viscosity means eta we have to find. Now let's solve this. How to solve? First of all, you see here what is given, and before that, let me draw the diagram so that you will understand what is there. Let us assume that this is a table. Okay, and here is a pulley, which is ideal pulley. Yes, somewhere here like this. And then we have one block, we can say. Particularly we should take sphere. Yes, so let us take it as a sphere. And here is a metal block. And now below this you have one liquid film. Okay, below this block you can see here is what? Liquid film. Okay, so this is what? Liquid film. And this is mass m is equal to 0.01 kg, and its area A is equal to 0.1 meters. Yes, no? Okay, so what is given, you see just first of all what is given here. F is equal to tension T is equal to mg, and that is equal to 0.01 into 9.8. So you will get 9.8 into 10 to the power minus 2. Yes, no? Because if you will draw the free body diagram, you have about tension, down you have mg, and this T is nothing but what? Force F, due to which it is getting displaced, right? So F we have this. Okay, right. Now area already they have given. Yes, what is area A? 0.1 meter square. Yes, no, 0.1 meter square. Next they have given velocity also. How much velocity? 0.085. 0.085 meter per second. Okay, right. And anything is there? Yes, they have given this also. Thickness means delta dx they have given. How much that is? 0.3 into 10 to the power minus 3 meter. Okay. So now how to find this eta? Yes. What is the formula of eta? Eta is equal to stress by strain rate. Yes, this we have learned yesterday. Stress by strain. You see once. Yes, no. This formula we have learned. No. F L by mu A, something like this. Yes, no.
Yes, sir.
Yesterday we have learned this, and that's why this strain rate, this strain rate is equal to, how I can write this, velocity by dx now. So you will get 0.085 divided by this 0.3 into 10 to the power minus 3. Okay, and this F by A means this mu by L is this, whatever it is. So direct I am writing now this F by A divided by this strain rate. Yes, no? Strain rate is how much rate? This whatever we got. So 0.085 divided by 0.3 into 10 to the power minus 3. And this F by A already we have or no? We have to calculate. So this is 9.8 divided by 0.1 at numerator, and this is 0.085 divided by this 3 into 10 to the power minus 4. This is equal to 9.8 into 3 into 10 to the power minus 4 divided by this is 0.1 means 1 into 10 to the power minus 1.
Sir, 9.8 into 10 power minus 2, no, sir. 4.
8.5 into 1 minute wait. 8.5 into 10 to the power minus 2. Yes, tell me.
Force is
Yes, yes.
9.8 into 10 power minus 2, no, sir.
Yes. We have to substitute that. Yes. So here minus 2 will come extra. Yes. Here you write minus 2 also. Okay. 9.8 into 10 to the power minus 2. So here one more 10 power minus 2. Okay. Now this minus 2 and this minus 2 cancel. This minus 1 cancels with this. So this is minus 3. 9.8 into 3 into 10 to the power minus 3 divided by 8.5. Check it now. Once you check, everything is correct. Check it once. 9.8 into 3 divided by 8.5. So I think answer you are getting 3.45 into 10 to the power minus 3. Okay. Pascal second. That is what coefficient of viscosity. Okay. Got it? Check it once. 0.003. Oh, yes, this is also right. Yes. Yes, right. You check it. So 3.45 10 to the power minus 3 Pascal second. Okay, everyone got? Shall I move ahead? Check it once. Everything is correct.
1 minute.
Do it fast. Do it yourself.
Yes, sir. Same.
Okay. Okay. Do it later. Let's move ahead. One more problem. You have to do yourself. A plate of area a plate of area 100 centimeters square is placed on the upper surface upper surface of castor oil 2 millimeter thick. Okay. Taking the coefficient of viscosity, taking the coefficient of viscosity taking the coefficient of viscosity to be 15.5 poise. Calculate horizontal force necessary to move the plate with a velocity of 3 centimeter per second. Okay, so see here, I'm just going to give you a hint. Do it yourself.
Sir, once turn back page.
You have to do it yourself, Ray. Once you got no, you can do now.
Okay, sir, got it.
So see here. Now area is given. A is 100 centimeters square. So this is 100 into 10 to the power minus 4 meter square. Check it once. Next one, on the castor oil thickness they have given, means dx they have given 2 millimeter. So this is how much? 2 into 10 to the power minus 3 meter. Next coefficient of viscosity means eta is given 15.5 poise. Okay. Next is what? Velocity also they have given. Yes. Means what? dv also they have given. Yes, no. So this is 3 into 10 to the power minus 2 meter per second. Centimeter per second to meter per second I did. Now what is our formula? F is equal to eta A into dv by dx. Right? Everything you have, do it yourself. Okay. We will move ahead. Okay. Okay.
Okay.
Anyhow, you are
Sir,
getting
1 minute, 1 minute.
YouTube link you are getting now. Don't waste time, Ray. You can write later also now. Leave some little space. Yes, finished. Yes.
Sir, okay, okay, done, sir.
Next one. Now, Stokes law. Stokes law. So see here. If a small sphere, of a radius r moves with a velocity, v through a fluid, of viscosity eta, the viscous force acting on it has magnitude F is equal to 6 pi eta r into phi, and this is what your Stokes law. Okay, this is what your Stokes law. This is Stokes law. Okay, so this force is nothing but viscous force. Okay, so viscous force formula is what? 6 pi eta rv. R is the radius of the sphere, v is the velocity. Now let's see in brief what happens in case 1 and case 2. Now let us take first of all case 1. Case 1. Now I am considering a tube. See here, I am considering a tube in which some liquid is filled. Okay, so let us suppose I have filled one liquid here in this tube. Now this is what a sphere whose radius is small r. What is the radius of the sphere? Small r. You can see here the radius of the sphere is r, and now this is moving down with velocity, let us suppose v. What is the velocity? V. Okay, now how many forces will act on this? Let's see. FBD, and in case 1, what is that case 1 also I will show you. So first you just see, this is free body diagram. How many forces are acting? First of all, its weight, that is what mg, which is acting in downward direction. Next you are having buoyant force, which is acting in upward direction. So this is buoyant force. And next you are having one more force which is in the upward direction, that is your viscous force, and that's why I am denoting it with Fv. So if suppose this weight is greater than this Fv plus this Fp, then what happens? This body will move down with acceleration a. That is what our case 1. When W is greater than Fp plus Fb. So this is what mass of the bob or sphere. Now see, from pre-word diagram what we are getting? mg minus this Fv plus this Fb is equal to ma. Check it once, right? And that's why if I want acceleration of this bob, that is equal to mg minus Fv plus Fb divided by m. So in this case, the bob will move down with acceleration a, and that is what this acceleration. So here sphere moves with acceleration a. Okay, this is what your case 1. Is that clear? Understood? Note down fast. Finished? Will you write later? Shall I move ahead?
Yes, sir.
Yes. Let's move ahead. Now you see the case 2. Case 2 is what? No unbalanced force. No unbalanced force. No unbalanced force means what you will get? W is equal to Fv plus Fp. Yes, no? Then in this case, sphere moves with constant velocity called terminal velocity. Okay, so if someone will ask you what is the terminal velocity, what you will say? What you will say for terminal velocity? What is the definition of terminal velocity? I am writing here. It is denoted by Vt. Okay. So constant velocity attained by body in a fluid when there is no unbalanced force. Okay, that is what Vt. And now if we will draw the free body diagram for this case, how you will get? See here, in the upward direction you have two forces as usual. In the downward direction you have weight. Okay, so here this is W, this is Fb, and this is Fv. So W is equal to Fb plus Fv. Now buoyant force formula, you know what is that? Density of fluid, rho into V into G. Yes, no? And that's why this volume of this sphere, that's why 4 by 3 pi r cube rho into G. Next Fv, you know what is Fv? 6 pi eta r into phi t, that is terminal velocity. And then this W is equal to mg, and this m also I can replace. How? Density of block is equal to m by v of block. So I can write density of block into volume of block into g. Yes, no? And that is again 4 by 3 pi r cube rho b into g. So let's substitute this, all values here. So for at the place of W, 4 by 3 pi r cube rho b g is equal to Buoyant force formula, 4 by 3 pi r cube rho into g plus this 6 pi eta r into phi t, because we have to find terminal velocity only. So now transfer here. So 4 by 3 pi r cube g I am taking common. So rho b minus rho, and direct I am dividing what 6 pi eta r, which is equal to phi t. So this pi cancel, 1 r cancels with this 6 and this 4, this is 2, this is 3. So you are getting phi t is equal to 2 by 9, okay. So this is 9, 2 by 9, this 3 and this 3, 9, okay, 2 by 9 r square g r square g rho b minus rho, and this eta also down, yes, no? So this 9 eta. Check it once. 2 r square g rho b minus rho and divided by eta. Check it once. Everything is correct. This is what your terminal velocity formula. Okay. Check it.
Yes, sir.
Okay. So note down this. We will stop here. Okay.